I still cannot come back from like I was planning this trip. Yeah. No, I told you. I told you that I couldn't find any way to
Okay, so we'll get back to the random systems that we started talking about before, so that we see that this kind of matches a real-world data set much more accurately. This looks a little more similar to the things we had with kind of the cell images. And this is what we'll use as then the starting point for the next tools that we'll analyze. And so we can look at compression just like we did before, where we now take our kind of default system, which has random points everywhere. We then apply a compression of 0.6 or a stretch of 1.5. And so we can see then in this graph that we had before, which is now much more meaningful, how those change. And so we have the points of all the arrows to the nearest neighbors still here, and the red, which shows that distribution, so where are the nearest neighbors actually placed compared to one another. And as we stretch that, we see that this object sort of uniformly gets bigger and smaller. And so if we go to the distribution of the nearest neighbor distance, we see that sort of the middle or the mean of this curve shifts. So as we go to compress it, it goes up to the left. And as we stretch it, it goes down to the right. And so it works sort of exactly the same way as it worked with the perfectly grid system, but now it resembles much better a real system. And we have a more meaningful orientation angle. So we see here as well that as we change the stretch, the orientation distribution does not change at all. So this might appear to be much higher, but these are all stacked on top of each other. And so in fact, we have exactly the same distribution that's just being lifted up. So we can now do something like shear. And on the grid system, the shear had a huge effect because we saw that they were only connected in one plane as we did this sort of middle shear step. And now, because the system's randomly oriented, we don't have this problem with sort of the nearest neighbors anymore. And so it's picking the neighbors that are closest to it. And as we start to shear this system more and more, we see the distribution for nearest neighbors doesn't actually look that much different than it did before. And so we have maybe some small changes. Certainly the angles are not the same as they were before, but it's not entirely clear that there's a trend of something that's happening as we perform this shear. And so that when we look at the nearest neighbor distribution, and now we use a density curve instead of a histogram to sort of look at the finer details, we see that there's kind of a slight shift, maybe, a little more of a bump that starts to come up down there. But other than that, it's very difficult to see a clear change in this as we perform the shear. We can then show the orientation, and rather than showing the orientation on a Cartesian graph, we can show it in polar coordinates to get kind of a better feeling of how that actually looks in real life. And we see that there are some differences, but it doesn't really have a clear trend as it did before. And so the shear transform, while it works very well on crystalline or quasi-crystalline structures, is very difficult to measure with the tools that we have in place now in a random grid. We can perform stretching just as we did before. So you have a 0.5, a 1, and a 3, where you get things closer to the edge or closer to the middle. And then we can start to look at how those graphs look. And we see here that kind of the number of outliers that we have does seem to change as we apply more and more of this stretch transform. And so the ratio of short ones to long ones seems to be different than it was initially. And so here it's very clear there's a lot more much longer nearest neighbor distances than there are in the untransformed example. But even here we see there's already more that are further away than there were in that original image. And so when we look at the distributions, we see that this stretch does shift this curve, but it also affects kind of this distribution. As we start to stretch more and more, we get more and more of a peak out there. And so it's not just a shift in the mean, but it's a change a little bit in that distribution, which for us means that if you have a sample where the mean shifts, but the distribution seems to be the same, then that's probably a compression. And if you have something where the mean shifts and there's a change in the distribution, that could mean there's more of this stretching going on, so that it's not uniform. It doesn't mean it's exactly this formula that's applying it. It just means it's not happening the same in every place in the sample. And that's what this stretch is approximating for us. You can then look at the distribution and you don't see a massive change in that. I mean, with randomly oriented structures, it will tend to be random before and afterwards. We now have the swirl system as kind of a final example, but this one isn't particularly important, where we see very little differences as we apply more and more of a swirl. And so here it's very clear that for a random system, using a nearest neighbor distance does not help us understand the swirl transform at all. So now we've been able to kind of quantify some of the differences that we've seen in these systems, and we've seen that there's a number of differences that are very difficult or not particularly sensitive to the nearest neighbor distance and orientation. And so that's why we now introduce some more tools. So this is the Voronoi Tesselation. And so for a grid of points, the Voronoi Tesselation looks like this here. There's some popular sort of iPhone and Android games that sort of play with this idea of a Voronoi Tesselation. But basically, it's a partitioning of the space based on a set of points. And so you have each point in your system, which is each one of these dots here, assigned a region consisting of that sort of the area that's closer to P than it is to any other point. And so for the small circles, that means this perfect grid. And so for us, we will call the area or the region around P its territory. So just to have a consistent term for this, this area here will refer to its territory. And as we can see, in a random system, this is much more interesting. We get a much larger distribution of what a territory actually means. And so this cell has a very, very large territory, and these cells here have very, very small ones. And so we can use this to actually calculate density. And so when we looked at the approach we had before of calculating density, you kind of drew little boxes, and you said, you know, there's 5 cells inside this box. Therefore, the density here is 5 per, square millimeter. But that metric didn't work very well because, if you move your box, if you shift your box a little bit, then the number of points that are inside your box changes. And you have to define how big your box is in order to get a meaningful metric. And now with the Voronoi Tesselation, we have a much better way of calculating the density because we see all of these territories are generated just based on this list of points. You don't require any other parameters or any tuning or adaptation to your system. And if you move one of these points a little bit here, the territory isn't going to change massively. And so this is a much more ideal way to calculate these kind of things because you don't require so many assumptions to go into your system. And so with density, the standard calculation is the number of objects over the total volume. And what we have for the territory is one object and a given volume or area. And so actually, we can now define a density for a single point by just taking the inverse of its territory. And so if you know how big its territory is, you can very easily calculate what the density would be. And so here, this one has a very, very big territory, therefore the density is very low. This point is a very small territory, and therefore the density is very high. So we can now color the points using this local density metric. And so here we now have these 4 different systems which we showed before. And we know the average density inside this cube is 500 points per square meter or square millimeter or whatever it is. But now we can color each one of these points with how dense it is locally. And so here you get, a dark concentration of very blue points because all of these points are very, very close together and are tightly packed. And then at the edge, you have a much lower density where those points have much more territory for themselves. You can then do the same thing, so you now get a very colorful representation of quantitative values that tell you about the density at each point. You can then start to look at how these distributions change. And so we see that the average for all of these is the same. So it's always 500 per meter squared. But the different distributions have very different curves for what the local density is. And as we see as well, the mean of this local density is not the same as the mean density. And does anyone know why that is? This is a quite important area of error propagation in physics or statistics. No idea. So we have here the density being 1 over the territory. And so the mean density should not be the same, or isn't the same in some of these systems, as the mean inverse territory. And so this is one of the very important things in physics or statistics when you do error propagation, that if you invert something or apply a transformation to something, the mean of that distribution won't necessarily be the same. The mean of 1 over x isn't the same as 1 over the mean of x. Which, if you look at a very simple example, is quite straightforward. If you have an object here for some reason that has a territory of 0, and you have other objects that don't have a territory of 0, then if you were to calculate the mean density based on territory, you would have one object that has an infinite density because its territory is 0, and a number of other objects that don't have an infinite density. But when you try to do an average of infinite and a bunch of other numbers that are not infinite, it's still infinite. Whereas if you have a very, very small territory or a 0 territory, but most of your other objects are positive, non-zero territories, your mean is still meaningful. And so it's important that when you do statistics or when you do analyses of groups, that the mean you're taking is the right value. And so based on the circumstance, it will depend on which mean you're actually looking at. But the mean of the inverse territory is much less stable than the total number of objects over the total volume. And so when you're looking at a whole image and you want to say the average density is X, you wouldn't calculate that from the territories. But if you want to define for a single point what the density is, it would make sense to look at the territories for that. Cool. Is that clear? This comes up in a number of areas completely outside of image analysis or processing, so it's a very important thing to know. That particularly when you're taking measurements, you can't, if you're measuring decibels, you can't just average the decibels together and have the average decibel, because the decibel is a log scale And so you need to transform it back to what the original one was, take the average of that, and then transform it back to the decibel scale. But to have it in that scale as an average would not give you an accurate representation of what's actually happening. So now the next thing after Voronoi Tesselation is sort of the counterpart to it, and this is called the Delaunay Triangulation. And so it's a really dual idea where you kind of make a triangle such that a circle which encloses this triangle contains no other points. And so you kind of go through each point in your system and draw these triangles so that you get that criteria met. And actually, the easiest way to think about the Delaunay triangulation is the neighbors of the Voronoi Tesselation. So if you look at this point here, there's a line there and a line there. And if you go back to this point, it's touching this one and this one. Or its territory is touching this one and this one. And so actually these two concepts are duals or the same. And so you can make this representation of it or the Voronoi Tesselation, but they have the same result. The nice part about the Delaunay Triangulation is that it gives you the neighbors. So with the Voronoi Tesselation, we got a territory, which is very useful when we're looking at things like density. But if we're looking at what are the closest neighbors to me, this triangulation makes much more sense because it gives you this actual topology of how your system could look. And so you can define kind of the number of connections you have at each point as the neighbor count or the Delaunay neighbor count. And what makes this advantageous to something like the nearest neighbor is that it gives you kind of the closest neighbor in every direction. And so rather than just giving you one neighbor for each point, it gives you kind of all of the neighbors. And so this is very helpful for looking at these systems that, you have this and you know that this point here is always kind of the closest point in that direction and is so close that it blocks out that point there. And so that point is no longer a neighbor, but both this point and this point are. And so now we can apply some of these metrics to real systems like we did before, where we have sort of compression and tension. And we can take our image and apply that compression and apply that tension and see how these change. And so here it doesn't look very differently. We see that these axes are now very different. And if we go to measure that, we'll see the results in a few slides. Shear is kind of the same sort of idea. Here is a low shear and here is a high shear system where we start to get kind of banding in this Voronoi Tesselation representation. And so we get very clear changes that we see as the structure goes from being sort of an unsheared to a very strongly sheared system. And with stretch, we get, again, very large changes that happen. And so this is what we'd actually expect because the systems that we were showing before, where we had the same average density and different density distributions, had the same sort of transforms applied to them. And so here we have a low stretch systems where things are near the borders, and there a high stretch system where things are packed towards the middle. Then swirl, which we'll leave out for now. And so we can now look at the neighbors in such circumstances. So if we take stretching and compression, we get these sort of results for the neighbors. Shear, we see some of those neighbors changing and some of the topology that we have in the system changing as well. And then swirl we'll forget about for now. And so now if we look at how actually these distributions change, as we apply a factor between 0 and 18, how do these values change? And so with the Delaunay triangulation and the neighbor count, nothing changes as we compress or shrink the system. which is something that's very nice, so that we have now a parameter that sort of encapsulates the system independent of its scale. So you know if this neighbor count distribution is exactly the same, then the topology has stayed the same. Of course, the lengths have gotten longer or shorter, but fundamentally, this structure that you have has not changed massively. We see with stretching that there's small shifts in this neighborhood count, so you start to move up this curve a little bit. With shearing, we see some changes happen there as well. And with swirling, we start to get sort of very weird behavior. We can then look at sort of the volume or the territory. We see with compression that sort of linearly or quadratically goes up. So as you increase this compression factor, you change your mean there quite a bit. We see that there's kind of the opposite trend almost with stretching. So your distribution gets shifted, but it gets also very much wider at the bottom. And with shearing, we see that as well, that we get a lot more points at this edge, swirling finally too. And so now we can start to look at sort of how does the mean change and how does the variability change of these different parameters as we apply these different transformations. And so what we have here is that sort of compression, the neighborhood count, the mean stays constant, the variability stays constant. So independent of what the compression is, that's fixed. With the stretching, as we increase the stretching, we see that that mean goes up, and we see that initially here the variability goes down and then it goes up again, which makes sense because 1 is kind of the unstretched state. So as we apply more stretch, the variability goes up. We see with shearing, the variability goes up, the mean stays more or less constant but changes a little bit, swirling a similar sort of trend. And so these are the kinds of graphics that can be very helpful for understanding what metrics or parameters could be changing in your system and what your actual experiment fits best to. And so when you do an experiment and you measure a bunch of these parameters, you can then look at graphs like this with more transformations that are better suited for the kind of system that you're looking at to find out, is the pattern you're seeing resembling something that you see here, or is it something entirely different? And so here, yeah, it's area and showing the same sort of pattern. But that if you're dealing with a system that you expect sort of to be uniaxially compressed, so it's like a bone sample and you're pushing down in this direction, you expect a compression in one direction and maybe not much of a change in the other directions. And so you could then replace swirling here with a uniaxial compression, make these curves, and then see if your experiment fits on these curves. And what's very nice about this is that you don't need to actually match one sample to the next. You can just look at the distribution of neighbors, the distribution of the territory sizes for all of the objects or pores in your sample, and use that to quantify what actually happened. Yeah, and so basically these parameters give us the ability to start to analyze some of these systems. And so if you understand the metrics of a random system and apply a known transformation, you can look at sort of how the mean or the variation changes in order to understand what's going on. Right. And so if we look at sort of a bone sample, you have a cell distribution inside the bone. The cell position appears to be random, and you want to show that the cells are consistently self-avoiding or stretched or something else along these lines. You can then use these kinds of tools to actually show what's happening inside your data. And so here we show a number of other different samples where we have sort of no compression, compression, tension. And then we can see how all those distributions change, and that if our goal were to measure compression very accurately, it's clear we would use this region territory because these have the most distinct peaks. so that even in a very noisy system, it would be unlikely that there would be too much overlap. This nearest neighbor distance is also very good, but there's these points that would be potentially difficult to see which one was better suited for identifying that or not. And then clearly these other parameters potentially could be used, but are much harder to then come up with clear sort of thresholds at this is when you would say it's compressed and this is when you would say it's not compressed. You can then do kind of a sensitivity analysis where with this you make many, many, many random systems and you compare the averages to each other. And that you see kind of with this regional territory, as you increase the compression, even in a very noisy random system, you still have a very clear trend at what's changing in your data. With nearest neighbor distance, it's there, but it's not quite as strong as it is here. And then with these other parameters, it's very low. So with stretching, you can do the same sort of analysis, that you have no stretch, squeezing, pushing. And the nearest neighbor distance and the region territories that we had last time, we're not particularly good at it, but we now have sort of these other parameters which could be useful. The Delaunay neighborhood count, or some of these other metrics. And then you can apply it and try to figure out which one of these has the strongest trend with your change in parameter in order to try to pick this would be the best, most sensitive metric to actually measure that change in the system. Shearing, we can do the same thing. So you make these graphs and then you see that this regional territory is actually the most sensitive metric we have for measuring how much shearing is taking place. Swirling is the last one, and we actually find that even though the transformation is very weird, this region territory coefficient of variation is the strongest indicator of that. And so we don't get a super accurate measurement, but it's the strongest indicator of the swirling effect. And so we could certainly classify non-swirled versus very heavily swirled random samples. And so this is not the best tool, but it would be the approach you would take if you were trying to quantify these kind of changes in a system and you didn't have another approach for doing it. So now we'll kind of quickly talk about self-avoiding systems. And so this is one of the other parameters that we mentioned, where we have this nearest neighbor distance metric, but this is very much linked to the scale of our sample. So as you scale your sample up or down, this nearest neighbor distance changes. And so how can we get a scale-free version of this metric? And so what we do is we say, what would the random distributed nearest neighbor be for this system if all the points were distributed with a Poisson point process? And so what we can do here is we can come up with this R0 as the cube root of the total volume over 2 pi times the number of objects as the expected nearest neighbor distance in a randomly distributed system. We can then compare that to the nearest neighbor distance that we have in order to get a self-avoiding coefficient. And so this now tells us for each point, if we've calculated the territory, how much this point avoids its neighbors. So this factor is then between sort of 0 and 2 or 3, I think. And so you get a useful scalar for quantifying, is your system organized in a grid where everything avoids itself very nicely, or are things packed together very closely? Cool. The last thing we'll go over, or the last major topic we'll go over, is this idea of a distribution tensor. And so this comes from the idea of looking at all the different points that you have in a system, and it comes actually from cellular materials, and how you can start to come up with a meaningful way to analyze this. And so instead of looking at each point as a shape, you look at a point and all of the other objects that it's connected to as an object itself. And so if you wanted a simple way to think about it, you have sort of like doing a shape tensor for the territory instead of the shape tensor for the object. And there's a number of objects where this actually makes more sense to look at the boundaries or the other objects around it rather than looking at the object itself. And so here, in this case, if you were to have this as like a liquid foam, and these are the center of the bubbles, that is the more interesting aspect of this isn't the bubbles themselves, it's sort of the boundaries and what other bubbles it's connected to, because those are the things that are putting forces on it and pressures and causing the bubbles to change rather than the actual shape of the bubble at this moment. And so what we have with this distribution tensor is that we do that, but instead of looking at all the pixels that are inside, we look at all the connections between the neighbors of the objects. And so we take all of these Delaunay neighbor edges, and we calculate sort of the covariance of that matrix. And so then we can do the sort of same eigenvalue transform that we did before, which tells us about the orientation of the distribution, and the scores then tell us about the corresponding magnitudes or lengths in that direction. And so what we see here is that if we take kind of these random systems like we had before, this distribution tensor gives us the ability to quantify how that looks in 3D. And so here we have a bunch of points. Here we have all of the links between the points. So this is like the 2D plot that we had before. And then here we have the distribution tensor, which we make from all of those links. And so what we see for this is that the distribution tensor anisotropy is 1%. And so we have randomly spaced points in a 1-to-1-to-1 ratio. And the distribution tensor is accordingly perfectly spherical, or almost perfectly spherical. If we now have points that are closely packed together in one direction, but far apart in sort of the other two, we can start to see that, this image for us forms kind of thin chords inside the image. So the distance is 2 in y and z and 1 in x. And that kind of forms strings because they're very close together in one axis. We can now quantify that by looking at the oblateness of this tensor and seeing that that's, 78%, and that's what structure kind of comes out. We can then do the same thing in sort of the other direction where you have a system that forms sheets, where it's very close in one direction, two directions, and very far apart in the other direction, and measure that with the same sort of tool. And so basically what this gives us is the ability to analyze these images and show how all of these points fit together. And so its interpretation is not very easy because you're never dealing with a real object. But when you're dealing with lots of points and you want to be able to say that they form sheets or that they form sort of lines or chords, this gives you an ability to kind of measure that. So yeah, you have a anisotropy here, which is just kind of how evenly spaced are the objects in your system. And, regular or grid-like or random distributions will all give you a distribution tensor, so it doesn't require that everything's perfectly grid-like in order to do it. And the oblateness can then tell you how this distribution in 3D actually looks. So when you have sort of this option between more strand-like structures or more sheet-like structures, you can use that oblateness term to measure how those cells or pores or objects are distributed in your system. So the real last thing that we'll cover now is this idea of orientation. So here we have a bunch of cells shown in red, and the orientation shown as these little blue arrows. And so what we have for these systems is we have the average, the standard deviation for 3 different systems. And I would say, looking at these, it's quite clear the top one is the most aligned, and the bottom one is the least aligned. But if you looked at the average and the standard deviation, there's some trend there, but it's not completely obvious. Here the standard deviation is 91, and for us it looks like it's completely aligned. And so taking the standard deviation of this angle isn't necessarily a very useful approach. So here you can show just the arrows themselves, as we showed a number of times, where you have the average as being sort of 79 and the standard deviation being 91. And so neither of those really correspond to what we would describe the system as. And so it's difficult. We create a system with an angle variability of 5, and we get a standard deviation angle of 91. And so how can we come up with an approach for quantifying this in a meaningful way? And here we can use the same exact tools that we've used for shape analysis and distribution analysis, where we now create sort of an alignment tensor, where we take all of the orientations in X, Y, and Z, and calculate this tensor for them. And so just like with the distribution, we got a tensor that showed if it was more strand-like or more sheet-like or more grid-spaced. We get here a tensor that shows how well-oriented the objects are. And so if your alignment tensor is incredibly anisotropic, that means that everything is more or less pointing in the same direction. And if it's incredibly anisotropic, if it's incredibly anisotropic, or if it's incredibly isotropic, then that means everything's kind of randomly oriented. And so your alignment is very low. So that what you get for this are then, the anisotropy here, where you take that tensor. Here's another couple of examples where you show the axis main direction, and then you measure the anisotropy of those systems. And that you can then show for a histogram versus orientation, you can calculate the alignment scores for each one of these systems. And you see that you go from having a 5, where the standard deviation of the angle itself is 91, to having the alignment being 98. And so you see that there's a massively higher alignment here than there is there or there. And this was not very clear when we had the angle that we were calculating the statistics for. You can then start to do this for many samples where you have lots and lots of different ways, and you can calculate here the alignment orientation and the degree of alignment. And so you can test this all on a number of different samples and sort of see how, as you increase angle variability, how the alignment changes. And so rather than having this standard deviation of angle, which sort of goes up slowly and then goes down again, we have a fairly consistently decreasing curve, which tells us how well aligned our system is. So for kind of the other approaches you have for dealing with these kinds of objects is you can start to use k-means to classify the point space. So just like you use k-means to classify the pixels, you can classify each of the points using a k-means segmentation clustering, which then groups them all together into different groups based on the features that you've calculated for them. And particularly when you've done a full shape analysis, you have quite a few features you can look at. And then the 2-point correlation function. So this is something we won't talk about very much, but this is really this ultimate tool that you eventually get to that allows you to quantify sort of any interesting distribution you might see in a system. And so basically what you look at is, given a point of type A at x, what's the probability of B at a point x plus r? And so it's a very sort of mathematical approach to modeling complex 3D objects, but it gives you a huge amount of flexibility in that you can choose what point type A means, and how you calculate this probability. And then you can look for sort of peaks and structures in your system which tell you something about what's inside. And so if you're dealing with cells and blood vessels, you can have the cells be, point B or type B, and the blood vessels be type A, and then you can calculate how are the cells distributed around a blood vessel very easily. You can also look for spacing of objects if you have sort of A and B is the same phase, that you can look at how they're related to each other. And just to have a few examples of that, we'll do this, and then this will be the last. So that if you have sort of a sample measured, which is a bunch of cords or fibers, and so they have a carbon core, a lower density silicon carbon layer, and then a higher density silicon carbon layer. That we sort of have, each one of these represents a different fiber that we're looking at, and we want to analyze them well. And sort of if you were to look at this and try to do a shape analysis or try to measure how thick this inner core is, it would be very difficult. You could probably try to segment these objects, but you see you get this object segmented as white, this one is blue, this one is green, and then maybe a thickness map would give you an idea of the average thickness there, but it would still be pretty tricky because you'd get the thickness of these objects out here, and that would kind of interfere with your final results and make it very tricky to extract a meaningful number from this. And so what you can do is you can use this 2-point correlation function in this example, where you say your object of type A is the core, and your object of type B is this blue material. And then you can calculate this function where you have the probability of having blue material as a function of how far away you are from the core. And so as you get further away, you can see this graph sort of slowly drops off here. And this is kind of the minimum inner layer thickness. So that now shows up as a very easy to mark point on a curve, rather than requiring having to go into all of these samples and analyze that manually. You can then start to see things like up to 10% of the surface is detached between the core and the inner layer. And so if you were using something like this to transmit power or communication, potentially this material would not be very well suited for that because you have lots of gaps in there where it's not being sort of isolated well. You can then calculate lots of other parameters in the system without having a very deep, intensive model where you're calculating or segmenting everything perfectly, because you're just looking at big probability distributions. Another system where this is very useful is like a compact clay. And so when you make a measurement of it, it looks something like this, where you have calcite, opinels clay, dense minerals, and they're kind of distributed all over the place. And if you look at this image, it would be kind of a nightmare to analyze. There's a number of different materials, there's lots of noise, there's not really a clear, object where you could say, I want to do the shape analysis of this, because that's just a big giant blob. If you did a watershed of this, you would break it up into a bunch of other big giant blobs, but you wouldn't really be any further. The only objects you could really analyze would be them, and maybe you could do some sort of spacing analysis between them, but it wouldn't tell you too much about it. And what we were really interested in this example in was kind of which direction did all the sediment compress in? And so are there layers in this structure? And how can we measure them easily? And so if you look at it, you can see that there's some sort of layer distribution here. And the other questions we had were kind of, if you take these pieces of clay or dense minerals, are they surrounded more by calcite or surrounded more by clay? Because that tells you something about the environment when it actually settled. And so both of those are questions that would not really be very easy with all of the tools we've covered up until now to solve. But if you use a 2-point correlation function, you can then see, your phase A is the distance from the dense interface. And then your phase B can be calcite in this yellow curve and clay in this blue curve. And you see that kind of right at the interface, you're surrounded much more by calcite than clay. And as you get further and further away, it sort of evens out. You can then also see that there's an asymmetry in the angle when you look at this function. So when you have this function, it's not just a radius, it's also an angle, where these two kind of come together, which shows you a little bit about how that layer structure might work. And now you can actually use a measurable angle rather than looking at the image and trying to make a qualitative assessment. So I think that covers what we want to cover for today. And then we'll do the texture analysis in 2 weeks with the next lecture, because I think we're quite good on time. So are there any questions on this topic? Yeah.
Is the triangulation.
Yeah. This one.
Yes, here. You comment, like you mentioned, that these two, like you made an example and you said these two are neighbors, but those two are not.
Yeah.
I didn't understand that.
Okay. So with the Delaunay Triangulation, you have sort of the easier example to look at would be, do we have that one? Yeah. Here, where this point, the diagonals are a little bit tricky, but this point is very clearly neighbors with this point and this point,
Yes.
but it's not neighbors with that point.
Okay, because if you make a triangle, you have another point.
Exactly.
Okay.
And so probably the easier way to visualize that is thinking about these territories, where it's like if you were to draw the territory around this box, where would that be and what other boxes could that touch?
Okay. Go back to here. What about the first, like the 0, 0 and 1, 1?
This one.
Yeah, that one and the 0, 0.
Yeah.
If you make a triangle, it's still a triangle without anything inside.
Yeah, so that's where you then have the issue that it either can be this one or this one, but it can't be both.
Oh, it's just like not uniqueness.
Yeah. And so when you look at, again, the Voronoi Tesselation, you either say that these two are touching or these two are touching, but if these two are touching, then by definition, they're preventing these two from being touching. So in most systems, you won't have such perfect symmetry where you have many objects which could actually all be touching. You'll normally have it very clear, because as soon as you move any of these points by a tiny amount, you no longer have that sort of symmetry problem that you're dealing with.
Okay.
So that when you look at the real system down here, it's then very clear all the points that it's touching or should be touching.
Okay. So when we have a line, it means that they are touching, like they are neighbors.
Right. And so probably another useful example would be like this point. We see that this point is neighbors with this point,
Yes.
and it's also neighbors with that point.
Yes.
And that's because they're on the edge, and so these 2 points can sort of touch out there, far away from the sample. And if there were another point here, then these would definitely not be neighbors anymore. And so you have a lot of interesting behavior that happens sort of at the edges that seems a little bit counterintuitive, but that's still the...
And that one is not touching with the lower one?
No, because it's far enough away and you can draw a large enough circle here where you're just at the edge of that circle.
Okay.
So the equivalent of drawing a really large circle that way is having a really large territory in that direction. But all of these analyses are analyses that are implemented and done. And so if you use Python or R or KNIME or any of these tools, they all have this built in. So it's not something you'll have to ever, or very rarely will you have to reinvent this. It's more about how to use it correctly to do the kind of analysis you're interested in. Okay. Any other questions? Or is that good? So yeah, so you can start working on the exercises. And if not, enjoy your Easter break. Thanks.